Hello, one and all. This is Glitch Failure here, and I saw this Trojan War riddle from TED Ed, and I just had to give it a try. Just a heads up, I have not actually seen the solution for this, but my stance is I use code to solve problems. So I'm not going to solve this riddle normally. I'm going to use code and have my computer solve it for me. So let's check it out and see how it goes.
The Trojan War has been raging for 10 years, with neither Greeks nor Trojans prevailing. Gods and humans alike are desperate for a break, so when a divine omen races across the sky, the two sides agree to a 10-day truce. From high up on Olympus, you've been waiting for an opportunity to bring this bloody war to its conclusion. When you go to consult the fates, they advise, should the peace last for a full 10 days, all will end soon. However, if the truce is broken, the ensuing battle will lead to 10 more devastating years of war. The fates' loom has shown them the exact conditions that will keep the truce intact. The Great Trojan Plain can be viewed as a grid of Greek and Trojan encampments. If they're organized in such a way that any Greek can reach any other Greek camp without having to pass through a Trojan camp, and likewise for Trojans, peace will prevail. Anyone can move to a horizontally or vertically adjacent camp, but never diagonally.
Okay, so first off, I'm already thinking about how to set that up. If it's going to be a grid, but it requires the path, like one camp being able to traverse only its own tents, I'll likely have to do some like graph shenaniganeries, which is not something I usually do for these, but yeah, that's a consideration.
The problem is, they're currently arranged like this. Tonight, you can use your powers to swap up to 6 pairs of camps that are horizontally, vertically, or diagonally adjacent. No camp can be moved more than once. Which swaps do you make to keep the peace?
All right, so I'm going to take a pause here. So one thing you'll notice is that the grid, it's like a 5 by, so it's 10 in terms of the columns, but it has 11 rows. So it's a 10 by 11 grid, and it has like this one camp that's kind of trapped by itself. So you need to make up to 6 swaps. Nothing can be moved more than once, and you can swap diagonally as well. So that's interesting. So the camps need to be arranged horizontally and vertically to all line up, but in terms of like movement, you can move them up, down, left, right, but also diagonally. All right, let's check out some code. Here is my basic algorithm of how I think I'll approach it. So the start of the algorithm is going to be a queue, which is basically just like a list where we're popping off until we basically have no more elements. And this queue is going to house the different states of the board or the grid for consideration. And basically, I'm going to initialize it with the same field that we had before. It's going to be like a nested list, probably like a list within lists that represent the field state. And basically, we're going to do a while loop. Just while the queue has elements, pop off of that queue. And then what we're going to do is check to see if the field is valid. And if it is, then we're done. We basically found a valid field. If that's not the case, then we want to create all possible valid moves from that board state. And so what that's going to look like is each position on that grid, I'm going to consider moving and swapping up, down, left, right, and then also all 4 diagonal positions. That's a total of 8 possibilities. Not all those are going to be valid all the time. We were told that some spots can't be, once you do a swap, you can't move it more than once. So that is how I'll approach that. One optimization we can also do is to store a cache. This can balloon out very, very quickly. Considering all the possibilities, it's going to be like an end-to-end problem, so we really don't want to deal with all that. So I'm gonna probably be using some optimization while I'm going through this. So here is a coding practice that I like to go with. I'm basically writing out my algorithm as if I had this code. I don't have this code right now. It does not exist. But if I did have it, this is what it would look like. I would create a cache, which is going to be helpful for optimizing. I'm going to create an initial field, which is the same one from the problem. We have a queue, which is just a list with that initial field. And then while the queue exists, we're going to pop off from it and then check, is this a valid field? Because if it is, then you're done. And we break and we're happy. Otherwise, we make all valid moves from that field. This is going to be a list of new fields. And for each one of those, we are going to convert it to a hashable form, which is a string in this case. So I'm going to convert that field to a string and then basically check to see if that's in the cache or not. The cache is basically used to see what has already been considered. We don't want to repeat ourselves. So if we happen to recreate a state that has already been considered, we don't want to have to go through that again, basically. So this is a way of like filtering and reducing the complexity of our problem. It's a minor point, but it's nice to have, so I'm going to include that here. Okay, so here are some like configuration considerations that I want to start off with. I'm going to use a character to represent the Trojan or Greek camp. I'm also going to represent a similar Trojan or Greek camp when the state of that camp has been that it's already been swapped. So if it's already been swapped, I'm going to use a lowercase t for a swapped Trojan camp, a lowercase g for a swapped Greek camp. I've also have a bunch of tuples here, which is just to help me with some later on logic. Basically, these are just like saying, hey, are you a Trojan camp? Either you're a capital T or lowercase t, basically. Same thing with Greek. And if you've already been swapped, then you're in one of the lowercase letters, basically. Here we're instantiating the width and height. This is going to be used for creating the field. I'm having it be a list of lists. First list is like the length of 11, which are the rows, and then the height of 10 is going to be the number of columns, effectively. We're told a max swap of 6, so that's going to be something I'm going to limit. And again, later on, I have some optimization here that I want to consider. So I have a total number of Trojans, which is going to be the width plus the height minus 2. And I'll show you why that makes sense in a second. So here I've created some simple functions. This one's called create init field, and it's just creating our initial field. This looks more complicated than it needs to be, but basically it's just a list comprehension where we're creating kind of like an outer list and then a bunch of inner lists based on the height and widths. And placing the Trojan and Greek tense accordingly. The one in the middle needs to be kind of manually fixed, but that's okay. So here, if we look at the initial fields and create it, we can see what that looks like. And you can see how it's just like a list of characters, basically. I thought this was kind of ugly to look at, so I created a simple helper function here, print field, and it takes a field object and just prints everything in a nice way that's nicely formatted for us to read easily. So let's read that and this one, and we can see that it's the same thing, just in a way that we can kind of see with without having to look at a bunch of commas and quotation marks. Okay, another helper function I have here is called field to string. Again, another simple function that's basically just concatenating everything in a way that converts the state of our field into a single string. And this is what it looks like. So this representation is exactly the same thing as what we have here, although it's in a single long string. So if you were to read the characters one at a time, left to right, and then concatenate it one at a time, you would get exactly this string. And what's nice about this is that this is a nice, succinct way of representing the state of the board, because this is how we can actually cache whether we've seen this particular board or not. What's nice about this problem is that we have distinct state where it really doesn't matter what happened previously. However you got to that state, it doesn't really matter how you got to it. So it kind of reminds me of a finite state machine in that way. Okay, so now I have a bit of a doozy. This is just kind of another helper function, but what we're going to do here is create a graph representing all of the neighbors for each position on our map. All I'm doing is creating a dictionary, and basically the key is going to be the current row, kind of like how it works with the list. So it's going to be very similar to how the list works. And you'll see this for loop is also working with that. The width is representing the number of rows. And then once you are at that row, we create another dictionary. So it's kind of like a nested dictionary to create the columns. And so we loop once again for the columns here. And once we get down to that, we are going to create a list, which is going to represent all of the neighbors for that position. So for example, if you have this graph and you put 0 and then another index for 0, 0, then what comes out is a list of tuples representing the row and column index for the neighbors. So all the neighbors around you, it just spits out that. I'll show you what that basically looks like. But here we have the up, down, left, right. I have here some just edge case bouncing logic to make sure that when we actually look for the neighbors, we have only the valid neighbors that are possible within the grid. All right, so what we have here, for example, the 0 is the first row, and then the 0 here is referring to the first column of the first row. And we see the lists here for that is 1, 0, and 0, 1. So what we're looking at is like the upper left corner. There are only 2 neighbors, and I can go up here again, and that's like this corner here. There are only 2 neighbors here and here, and that's what those numbers represent. It's a tuple of the row and column position for that neighbor. And this graph is going to be helpful because later on it just allows us to quickly grab who the neighbors are for each spot without having to do all this like bouncing logic or whatever. So this is just like this, having this graph is just a helpful object to have. Next, I have another function. This is getting way more complicated, but anyway, here is a function called field is valid, and it takes a field and it will just tell you if the field is a solution, basically. Have you found the solution, true or false? And what I need to do is first find a Trojan location and a Greek location, and then kind of see, as that starting position, find all the neighbors and see if you can find all the Greeks or all the Trojans accordingly. So the start of this logic is just about finding a Trojan or a Greek tent. You need to find both of them, basically. And so all this is doing is looping through the rows and columns. If we don't have a Trojan location and this position is a Trojan camp, then bam, we found a Trojan location. Same thing with the Greek. And once we found both, we can just break out of this loop because we're basically done. That's all we need to do is just find a single Greek and Trojan camp. Now, once we have that, we're going to use the graph logic. And so I'm going to explain this a little bit. But effectively, we're going to keep track of all the Trojan tents we visited as a set. And I'll be explaining that in a little bit. It's basically kind of like a cache in a way. We're going to have our Trojan queue, starting with our initial Trojan location. So I guess I like queues and caches. This is kind of the same logic from the main algorithm. But basically, while we have Trojan queue, that means that we have neighbors that have not been seen yet. That's all that's referring to. So we pop off from the queue. We stringify that tent location. This is a tuple. Remember the tent here, when we pop off, that's going to be like a row and column index. So it's going to look, it's a tuple with those 2 values. So if we stringify it, and I'll show you an example of that real quick. 1, 2, that's tuple. If I wrap that with, if I convert that to a string, it's just a string 1, 2. So it's a quick way of representing a unique tuple, basically. Once we do that, if we've seen it before, if we've seen that neighbor before, we don't need to consider it again. So we just hit continue. Otherwise, we deconstruct the row and column, and then we find to see, hey, are you actually a Trojan tent? So this Trojan queue has only the row and column, but we don't know what the actual value on the map is. So what we're looking to see is, hey, fields, grab the row and column, what is the actual value at that position? And if it's not one of the Trojan camps, then we don't care about it because this logic is only for the Trojans. Otherwise, we do want to consider it, and we add that to our visited set. Again, we're going to stringify the row and column, and then we're going to add our neighbors to the queue. But what are the neighbors that we need to add? Well, here's where we're using the graph. So we're going to grab the neighbors, and remember how we get the neighbors out of the graph. We put the row and column for that particular spot, and the value for that is going to be a list of all the neighbor positions, their row columns, their row and column indices. And so here I'm just doing Trojan queue with the extend, which is just going to add, just append the entire list. That's a way of adding a list to list, basically. Once you're done with this queue, you found all of the neighbors linked to the initial Trojan. And what's good to know is the length of the visited Trojans, which is that set that we had, if it's less than the total Trojans, then we haven't connected all the Trojans together. So we can kind of stop short. So this is us like stopping early, because I don't need to go through more logic to know that this is an invalid situation. So what I'll be returning here, and you'll see why I would want this later, I'm going to return the length of the visited Trojans. So ideally this is going to be as close to the total as possible, but in this case it's not, and we return false. So this is going to return two things: the number of connected Trojan tents and the state of whether it's a valid field or not, in this case false. If we get past that, then we have all these Trojans that are connected, and then we can check the Greeks, see if they're connected. And all this is the same logic for the Greeks. And in the end, our result is going to be whether or not the total connected, so that's the number of Trojan tents and Greek tents all visited, it should equal the width times the height, because that's all the possible spots basically. And so it will return, I want to be consistent with what I return, so I'm still returning the length of the visited Trojan tents, which at this point, if you got to this point, then it is the total Trojans. And the result, whether it's true or false, is determined by this logic here. All right, so let's run this, and we can actually try it out because we have a field already called the init field. So let's see if this works for the init field. We get 5 and false. So 5 Trojan, that's probably 1, 2, 3, 4, 5. So maybe it's this column here or this row here. Either way, it's 5 connected, but not all of them. And how do you get all of them? You get 5 plus 5 plus 5 plus these 4. And that's basically a full length of the column and a full length of the row, but you minus this centerpiece once, but then twice, because you're doing it, they're overlapping. So that's why this is how you get the total number of Trojans. The width plus the height minus 2. Okay, so I had to go real long on this one. So in the end, I want this function called make all valid moves from a single field, and it requires a bunch of stuff happening. That's why I've kind of broken it up into these helper functions. I will go over each one individually though to start. So here we are going to check to see, are the max swaps reached? So this is going to return a Boolean true or false. Have you reached the maximum number of swaps? This is important because we're told that there's a limit. So once we go past that, we don't want to consider anything, that it wouldn't be valid to have any more than that, right? So what we're going to do here is we're going to keep the number of swap tents at 0. We're going to go through the height and the width, which is the whole field basically, grab the tent, and we're just saying, hey, are you a tent that has been swapped? If you are, then add. So this is going to be a Boolean, true or false, which to the computer is the same thing as saying 1 or 0. So when I say plus onto this integer here, that's basically like me saying add 0 or 1. If it's false, then it's not going to add anything. If it's true, it is going to add a 1 to that. That's a little shorthand for you. Once you're done with that loop, you will divide by 2, because the numbers that are getting swapped is basically double, because you're swapping 2 things, right? So the number of swaps are going to be 6, but the number of actual tents that are swapped are actually 12. So I'm going to divide by 2 and just return whether the number of swaps is greater or equal to the max swaps, because that will be whether you've actually reached your max swaps or not. The next helper function I have here is called are swappable tents. It'll get a tent, in this case like a T or a G, and it's just going to return true if they are swappable at all. So the first thing I'm checking to see is tent 1 or tent 2, have you already been swapped? If that's the case, then no, they're not swappable, so that's returning false. If they are both from the same tent, the Trojan tent, then there's no point swapping them, they're the same thing. So there's a false for that. Same thing with the Greek. Otherwise, we return true, because at that point, it's okay to swap. And now we get to the big function here called make all valid moves. It will take a field, and here I'm going to instantiate all possibilities as an empty list. And here I'm using that max swaps reached function. So if the field has already reached its max possible swaps, then we just return an empty list, because there are no more valid moves allowed. And here I have kind of like an inner helper function. I know that I don't do this very often, but I felt the need in this particular case. This is just going to do the swapping for us. But what we're going to do is we're going to create a new possibility, right? So we're going to take the current field and make a copy of it, what's called a deep copy. It's a nested list, so we want to make a deep copy. So anyway, it's just, this copy is just a copy of the field. And now we have that copy, we can make changes to it. And so here I'm taking location 1 and location 2, which are the row column. It's a tuple. Each one of these is a tuple of the row index and the column index for the first 10 and the row and column index for the second 10. And basically this logic is just like swapping the two from the copy based off of what was actually in the field. And then what you want to do is make sure you're not using the capital T, because it's now this is the swap, right? So here we don't use capital T, we use a lowercase t if it's a Trojan camp. Otherwise use the lowercase g for the swapped Greek camp. And the same thing for the other position. So you're just like, again, you're just swapping whatever is there, you swap. And then I append to our possibilities whatever that new copy is. This helper function is going to be used later on, but it's nice to have it here because we're altering this list, but I want to keep the logic kind of in nice encapsulated ways that are abstracted, and I like it. I like having it like this. What I have next is I'm going to go through each row and column, and that is going to require now us considering all the neighbor locations for a swap. So there are 8 of them. So what we have here, and I originally had it hard coded, but I thought, why am I hard coding 8 individual things? I could just abstract this into like this list and just loop through that list. And that's a lot easier. And so what I have here is a list of the neighbors that could be swapped. So here is going up, down, left, right, up, left, up, right, down, left, down, right. And these are all the positions that you would want to consider. These may not all be valid. Some of these might go outside the grid, but I don't care about that right now. I just want to make sure I have all possible neighbor locations, row column indices, for consideration. Then I grab the tent of the current spot. And here I'm looping through that neighbor locations list. So for each one of those, I've destructured the neighbor row index and the neighbor column index. And here I'm doing my edge bounce check, essentially. I'm checking to see that the row index is not less than 0. Same thing with the column. And also that the row index is not greater or equal to the width. Same thing with the column for the height, though, because the height is for the columns, right? So if that's the case, then we just continue. We ignore that particular neighbor. Otherwise, we do have a valid neighbor swap, potentially. And what we want to do is then grab from our field that neighbor, the neighbor tent, which is going to be a T or a G. And we're going to ask, hey, are you swappable? If they are swappable, then we do the swap. And that's what this logic here is doing. Here is the add swapped copy from that helper function from earlier, which is just going to take the location of one tent, which is the current tent, row I and column I, and the neighbor's row index and column index. Once you get through all the possible elements in the fields that are swappable and you've populated our possibilities, that is a list of all possibilities, you have a bunch of copied fields that have those swaps already done, you can now return those possibilities. So now we're basically done. We just have to put it all together. Okay, so this one took a while. I am making my life a little easier by importing this helper library called heapq. This is a default Python library, which I'm using to essentially create a priority queue. I have actually already made a video on how to build a priority queue from scratch, so I'll link that somewhere up here. But essentially, I'm just making my life a little easier by using something that's built in. This algorithm looks very similar to what I had earlier. There's a slight difference using the priority queue, but for the most part, it's very similar. Just to show you what this heap queue looks like, basically you would have a list. Let's say I have a list of a bunch of numbers here as L. I'll import heap queue, and then what I want to do is called heapify on L. So what heapify will do is it'll look at the list and make in-place changes to create the structured tree representation of a heap using that list. So if I run that and I look at what L looks like now, you'll see that it looks like it's been changed, right? So this now has the smallest value first. So this is effectively the top of the heap. And the way heapq works, if you look at the documentation, it actually uses the smallest value. We don't actually have a different object here. This is the list, it's just a list. But when we want to do priority queue things to our list, we don't do it manually, we have heapq do it. So for example, if I want to pop the top value from the list, that's heapq, and it's called heap pop, like that, you'll see it gives me an error because we have to supply the one argument, which is our list. So the list object is the thing that's housing all of the values, and we popped off the 12 from it. And so if we look at our value now, we see that we're missing the 12 because it's now the lowest value now is the 79. So that is what I'll be using for my algorithm. Okay, so first I'm going to create a cache, which is just a set. I'm going to create an initial field, and I'm going to add it to our priority queue. And you'll notice that the priority queue actually has a tuple. I'm instantiating it with none here, but effectively this is the priority. So I can make this like whatever I want, really. The first time it doesn't matter because there's only one value. So what does it matter what priority it is? So we can put like 99 or in there, whatever. It doesn't matter. And the init field is the second value. The reason I'm doing this is because the way heap queue works and the way priority queues work, it's going to try sorting. It needs some way of sorting things. So the reason I'm doing that is we're going to need some way of determining what is the lowest priority. And the way you can do that, there are a few ways of doing that, but I'm basically kind of hacking a little bit by using the tuple and how it will sort using the first value. So if I have a list of values, like 99, B, and 5, C, so it's a list of 3 tuples right there. And if we have a list and we say L.sort, well, what is it going to sort on? Is it going to use the value A, B, and C, or is it going to use the 199 and 5? So if we sort it, you can see that L is now sorted in place using the first value. So the way tuples will work when you're sorting them is it uses the first value. It assumes that that's the thing you want to sort with. So that's what I'm using for the heap queue because it needs to know what value is less than the others. And that's the idea. So the first value the first time we instantiate doesn't really matter. That's why I'm going to leave it as none here. And here I have a variable called solution found. That's just to help break early once we found a solution. So while we have values in our priority queue to consider and we don't have a solution, we're going to just keep popping basically. So we're going to pop off, but we're not popping using the list pop. We're going to use heap queue heap pop, which is just basically taking the smallest value of the list, the lowest priority basically. And I'm going to destructure it because I basically want to get rid of the priority. At this point, I don't care about it. And the only thing I care about is the field. So I'm going to take that and I'm going to make all valid moves from that field. So earlier in my logic, I had a check at this point to see if this field is valid, but I ended up swapping it to being later on because I actually want to tease out the priority using the field is valid because I'm able to count how connected essentially the field is, and that's important, and I want to use that for as essentially a way of saying well that's the priority. But anyway, I'm getting ahead of myself. So I've destructured the field here. We're making all possible moves, valid moves. So this new fields is a list of new fields, and for each one of those fields I'm going to check to see if that field is valid, and I'm going to also tease out the priority for that. So that's again, the priority is just a way of, it's like an objective function. It's looking to see how good is this field. And I want to prioritize the fields that are very well connected. That's the idea. And so if it is valid, then we found a solution. We're done. That's very easy. I'm going to print the field. I'm going to set solution true, and I'm going to break. And then, the while loop will also break on itself because it's checking to see if that's true as well. If otherwise it's not valid and we want to keep considering things. And so what we would do is we convert that field to a string, and this is the string representation that we're going to use in the cache. And we just check, hey, if the field is not in the cache, then we're going to add it. Again, we're adding the string version of it. And then what we'll do is we'll add to our queue. And again, we don't add directly to the list. We use heap queue to do that for us using the heap tree structure that it understands and will, put things in the right place. And I have my priority queue, which is the first argument, which is the actual list itself. And then the second thing is a tuple of the priority and the new field. And that's, again, how we're destructuring it here, because I want to have a tuple that has the first value being the priority. Notice here I have priority being negative because of how the sorting is working. The lower the number, the higher the priority. And the way I'm creating the priority is by counting how many tens are being connected. So in this case, the higher the number is good for me. So in order to have it be set as a priority, I need to make it negative. That's all. And then we add our new field. And once we are done with that, hopefully we'll have a solution. And there is a lot of optimization going on here. So this is definitely running quicker than would be normal if I were just considering all possibilities. The priority queue helps a lot with that. So with that in mind, let's run this cell and see what happens. All right, well, that was pretty quick, instantaneous. Okay, so let's check out this solution. It looks like, so remember the lowercase letters means that it was swapped. All the capital stuff has not been changed, basically. So we see that the center one has been swapped, and I guess it must have been swapped here. So that's one swap. And it looks like these used to be T's, so these got swapped, but it got swapped like at a diagonal here. So these got swapped at a diagonal, and you can see that all the T's are connected here. All these T's are connected, and now the G's need to be connected, and you see there was a swap here. So it looks like the G got swapped here, so at kind of a diagonal here. So the T is connected this way, and the same thing happened up here. The T got swapped over here. So it kind of created like a little hook that allowed all the G's to be connected. Notice that there's no connection here though. Like all these T's are connected here, so the G's can't go there. But the G's can go all the way around on this end. And then we see another G over here that is connected. So that is how the solution looks. Let's see. I spent longer probably building this coded solution than if I were to try it on my own. But you know what? That's not a problem. The computer now can do it. And what's nice is this algorithm will work no matter how large the grid is, right? And you can give it all kinds of weird input. So I believe that even though this one particular problem I could have solved quicker manually, I now have a solution that is generalized for anything. So, haha, that's better, I think. So let's see what they say on the video.
The first insight here is to divide this into two sub-problems. There's the matter of connecting 4 clumps of Greeks without putting holes in the Trojan line. And then there's dealing with the thorny center space. Let's consider the Greeks first. To connect any Greek clumps, you'll have to mess with the nice, straight Trojan lines. If you try to do that anywhere in the center of these arms, you'll create new, isolated clusters of Trojans. So the only option is to go to the perimeter of the field and move some Trojans diagonally, say here, here, and here. Now for the center. There's no way to connect the Trojan arms without swapping a Trojan in. But continuing to shift that arm of Trojans inward would require moving the same Greek camp multiple times. However, you could shift the whole Trojan arm up and to the right, closing this gap. There are several solutions with slight variants, but as long as you perform this maneuver on the short arm of Trojans, you can achieve peace in exactly 6 moves. You make the swaps and all is well until...
You know what I should have done? I didn't realize until just now. I should have found all the solutions, right? Like there's not just one. I just stopped I stopped early because the problem kind of balloons out to a very large number. So I didn't want to like go through all that. But yeah, there are multiple solutions to this for sure. And you know, when I was thinking about like how I would solve this manually, I was thinking that the shorter arm there was something to do with like the shorter arm because there are only 4 on the left side there, and 5 everywhere else. So I figured there's something there, and apparently that's the trick of it. Like that left arm needs to be all those need to be moved. So that requires 3 all by itself, and then you're moving the centerpiece and then only 2 of the outer arms. You'll notice that there's still 1 that's connected. So yeah, so I'm glad that this I should have tried thinking about like all the possibilities, but live and you learn.
Till the 5th night, one of your rival gods wants to see the bloodshed continue and has taken advantage of a forgotten prophecy. He's convinced one Trojan camp to make a swap with their horizontal, vertical, or diagonal Greek neighbors that will break up the Greek connectivity. Once again, you consult the fates, who prophesize the following. The meddling Trojan camp is somewhere within 4 grid spaces of the perimeter of the battlefield. They won't go through with a swap if it only breaks up Trojan connectivity. And finally, you can make at most 2 swaps with the same rules as before to thwart them. Which swaps do you make to block the troublesome Trojan camp?
We have a second riddle. Oh my goodness, I did not see this coming. Okay, so more coding, I guess. So I'm going over the second part now, and I wanted to fix a quick bug in the field is valid function. It's a kind of small one, but I'm going to go up and show you what I'm talking about here. So in my field is valid function, I had some logic here that was like If not, if there is no Trojan location and the tent is Trojan tents, then do this, else do this. And the problem with that is that I'm checking for two conditions here. So if even one of these are false, like let's say that there is a Trojan location, then this may be true, but the else statement was catching all that. So I wanted to make sure that I'm correctly implementing my logic here, that I want to make sure that there is no Greek location and the tent is a Greek tent, and therefore I'm instantiating a proper Greek location. Secondly, I just copy and pasted my solution code and changed one thing. The solutions found is now a list, and now I'm gonna keep looping and doing my queue up until the point that I have 15. The reason for this is that in the solution that I just saw, there were 15 possibilities, solutions there that were valid, or at least that's what they said. There are probably more, but I'm going to use 15 because that's what they gave me. And I'm just populating that list. When I find a solution, I just add to it and I just continue. So up until the point that there are 15, then we stop basically. And I found a bunch of solutions here. So interestingly enough, there are at least 15 at this point, and I'm looking at them and trying to figure out what the deal is. I'm not going to actually necessarily code this out, even though I have 15 solutions. It would be kind of easy to code, but I think it's even easier to manually look through it because there are only so few solutions. And whatever solution we find, we have to realize needs to be generalizable to all of these solutions because of the fact that we're told that there are multiple solutions, yet this second part can be solved, it can be used for all of them. So whatever I'm looking at, it needs to be generalizable. So, okay, the thing that they all have in common is the left-hand side, always, you have to move all of them basically. Including the center. So the center and everything to the left needs to be moved. So that already has been swapped. So every solution has to have that. The other part of the solution is that two of these tails, two of the three tails need to be swapped with a vertical swap. A diagonal swap. But it doesn't matter which one those are. So my assumption is that it's got to be something about one of those three things. It's got to be that's the solution. It's got to be in there. Okay, so we're told that the defecting camp will only make the swap if it results in some Greek soldiers being unable to move, and the Greeks are the majority, so they're the yellow ones here. So in my solution here, they're they're the bigger camp, right? So the thing to note, and I didn't know this earlier, was that there is always one tail that's attached all the way. So I'm assuming that might be part of it, because in order for the Trojans to have continuity but not the Greeks, I think they would want to close up this little hole here basically. So they would swap back essentially. So what we would want to do is to make sure that there's always an opening. And what that looks like is to open this one up. So I think I would swap this one diagonally. So that's at least one swap. Anything else would break the Trojans, right? The Trojans are in a line essentially. So they can't just go swapping anywhere they want. So it's got to be move this one diagonal here or here. Oh, there's only two Trojans, right? Or sorry, there's only one defecting camp. So I think I can move just one. I think you only need to move one. Maybe I'm wrong about that. I think you just need to move this whatever the attached end is, make sure to move it diagonally with one of the Greeks, and that should do it. Okay, so I think that is my possible solution. Let's find out.
You won't be able to identify the scheming camp precisely, but there's a lot you can do to at least narrow down the options. They have to be somewhere in this area, and they have to be able to block Greek camps from each other in a single swap. That doesn't leave many options. The only possible blockages are at the end of these two arms, where a Trojan camp could plug a hole without opening a new one. So they must be in one of these four camps. Let's look at the right arm first. There's a threat here because this column has two Trojan camps. If one moves to the right, the other will still be in place, blocking Greeks from crossing. So we can thwart them by moving either one a column left into this square, and the same principle applies to the bottom arm. Your effort maintains the peace for the final 5 days, but it seems that a certain Greek general noticed what was happening and left the Trojans a parting gift.
I'm not too sure about that, right? You don't need to. I don't think that's right. You don't need to swap two. You can just swap one, because effective. So there's only one camp that could close the gap, right? That's this one here, or this one going here. And all the solutions have that. All the solutions have two curled end tails that are keeping an opening, right? So whatever is attached is still allowing the Trojans to all be attached while still allowing the Greeks to flow through. So I disagree with their solution. I don't think you need two. I think you can just make a single move, because no matter what camp is malicious, either like the thing that like the camp I just moved, if it tries to close the hole, it doesn't matter. We still have two openings. Like, that's the point. There, you need to allow for two openings, three openings, but the left one can't be closed, basically. So two additional openings will allow for all the Greeks to traverse. I'm not sure if I agree with that solution, but anyways. All right, folks, that is the end of this TED riddle. If you have any other suggestions for riddles or any other way I can like use code to solve a problem, I love that idea. So, definitely leave a comment. If this is the kind of content you enjoy, please make sure to like, subscribe, do all the good things, and I will see you next time.